Okay. Now, even I had forgotten to record, but I think you follow up from what you have just drawn here. So we are using an extended object. Now we are finding FP. So FP, what's the distance of FP? FP is the focal what? The focal length F. Are you seeing that? So we shall write FP as F. So I can write FP as F together. Then let us look at another. We are looking for FO. FO. So what is FO? How do we get FO? So to get FO, we must get OP, OP minus P minus FP. To get FO, we must get OP, this distance, FOP minus minus FP. So it means that for me to get FO, I must have the way I've seen in the diagram there. For me to get FO, F to O, I must get OP minus FP. So it is OP minus FP. OP minus FP. And OP, I want you to see very well, OP in our diagram there. What is OP? OP is?
U.
Is U. So I'll have U minus, and what is FP? So what is FP?
It is F.
It is F.
It
Correct.
is F.
Now, I think you have drawn the diagram. So how about Fi? How do we get Fi? Stephen, are you there? Okay, Stephen, your network.
Yes, teacher.
Okay. Have you drawn the diagram, Stephen?
Yeah, not yet. Stephen.
So how do you get Fi? So to get Fi, this is Fi, this distance here, Fi. So to get Fi, I must get Ip minus Fp. Are you seeing that? Fi is Ip minus Fp. So I have to get Ip minus Fp. And Ip is the image distance, which is V, minus Fp, which is also F. All right. So now I'm going to substitute this, and this in this expression, which is here. So it means that my Fp is F. So I'll have F out of Fo. Fo is U minus F equals to Fi. Fi is V minus F over Fp, which is F. So there I'm going to cross multiply, and I'll have F squared equals to V minus F into U minus F. So I'll get F squared, which is equal to V into U minus F, then minus F into U minus F. Okay, hope you are following. So I'll get F squared is equal to, open brackets there, get UV or VU minus VF minus FU minus O plus F squared. So this F squared and this one, without, in other words, you get 0. If you bring F squared this side, you get 0. So this means this side I have 0 equals to VU minus VF minus FU. Okay, now what I want is that I want to get 1 over F. So I will take this one, which does not have F this side. I bring this side, or I can take these ones which have negative. I bring them this side, and I will have VF plus VU equals to VU. VF plus FU is equal to VU. So from there, I can write it again like that, such that if I decide to divide through by VFU, 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 all through by VFU, then it means that here I'm going to remain with 1 over F is equal to 1 over U, then plus 1 over V. And that gives you the correct expression for the mirror formula of a concave mirror, Okay. So members, are you there?
Yes.
All right. So the other thing that we should talk about, so you have questions. There are questions that can be asked to you. I was looking through in a question bank. They are saying that use the diagram, they are saying that draw a ray diagram to show the formation of a real image of a real object by a converging mirror. Draw a diagram. So the diagram you can draw is this. You can draw that diagram, and because it has Roman number 2, they're asking use the diagram above to derive the expression of 1 over U. 1 over F is equal to 1 over U plus 1 over V, where U, V, and F are object distance, image distance, and focal length. So you can go and check in 2001. There is that question which is there. 2001 number 2B. 2001 number 2B. So you check that question. It needs you to derive this expression which is here. Okay, now let us look at the sine conversion. The sine conversion. Sine conversion. Sine conversion as applied to spherical mirrors. Spherical mirrors. Okay, so the first sine conversion you should know is that the sine conversion, first of all, states that the sine conversion, it is S. The sine conversion states that real is positive, and virtual is negative. Okay, then the other thing that you should know is that the second thing that you know is that real objects or real or image distances are always positive. So real objects or image distances are always positive because real is positive, and virtual object or image distances, they are negative. So real object can be real, it can be virtual. So if the object is real or the image distance is real, then it is positive. So if the object is real or the image distance is also real, then it is positive, then it is a positive distance. That's what you should know. So if the image distance is real, then it is a positive distance. And a virtual object or image distance is negative. So something that is virtual is going to be negative, and something that is real is going to be positive. Then thirdly, the thing that you should know is thirdly is that if the focal length of the object and the image distances are positive, then you know that we are dealing with a concave mirror. So a concave mirror has focal length positive, and the object distance positive. In normal circumstances, they are positive. But if the image distance and the focal length are negative, then you know that we are dealing with a convex mirror. So a concave mirror, comma, concave mirror, the focal length, comma, object distance and image distance are real. We can say maybe in normal what? In normal circumstances. In normal circumstances. So the focal length, the object distance, and the image distance are real. Then there are those other abnormal circumstances. I don't know whether you know them for the focal, for the concave mirror, where the image distance is virtual. Sandra, when do we have the image, a virtual image distance in a concave mirror? Sandra. Stephen. Sandra, are you there? Sandra, are you listening? People can decide to mute. When I ask you questions, I've asked you, when do we have a virtual distance, or when do we have a negative distance, image distance for a concave mirror? When do we have that, where the image distance is virtual or it is negative? When? You have forgotten. Stephen, do you remember?
When the distance of
When do we have that?
When the distance of it is vacuum.
So when is the distance vacuum for a concave mirror? When do we have the image distance vacuum? At what circumstance do we have the image distance virtual? When the object is placed between what and what? Members, when the object is placed between? Sandra went off. Sandra, are you there? Or I put you in the what? I put you in the waiting room. Sandra, are you there? Okay.
Okay. Teacher, it's between the focal length and the focal point and the pole of the mirror.
Okay, as it came from very far, Sandra. Eh? Okay, that is true. So whenever the object is placed between F and P, the image distance will be virtual, meaning that the image is formed inside the mirror and it is erect, it is upright, it is magnified. So in normal circumstances, we have said that the focal length and the object distance are going to be real, and also the image distance will be real. They will be positive, but in the other circumstance, the one we have talked about, the image distance is virtual. Then, how about for the convex mirror? Convex mirror, comma, image distance, the image distance, comma, the focal length, and radius of curvature, and radius of curvature are all negative, are all negative. This one we don't have to say under normal circumstances, or I should know that they are all negative. Why? Because when you look at the notes here, what this diagram we've just drawn here, if I may zoom in here, you can see that here the R is inside the mirror, the V is inside the mirror, and of course, if R is inside the mirror, it means that also F is somewhere here, and it is also inside the mirror. So they are all negative. They are all negative, and they are virtual for a convex mirror. Okay. So that's what you have to note. So when you are calculating and you are looking for F, R, and V for a convex mirror, then you must get the final answer as negative. Negative, and so you should know that if you get the final answer, which is negative for the, let's say for the image distance of a convex mirror, then you should know that you are dealing with a convex mirror. So for the convex mirror, the answer you get will always be a negative for the image distance. If at all you are calculating, then you have to put the V as negative, and also you have to put the F as negative for a convex mirror. You have to indicate them. So that's why even in our derivation, when we are deriving this kind of derivation here, when you reached at this point here, somewhere here, we introduced negative R and negative V because we know that R is negative and also V is negative. So when you're calculating and they have given you that the image distance was found to be 20 centimeters behind the mirror of a, behind the pole of a convex mirror, then you put negative on the 20, and then you have your V as equal to negative 20 centimeters. So you substitute negative 20 in your calculations. Are we together? Members, are we together? Okay, that silence means that you have understood very well. So that is the sine conversion. So this is what they try to summarize for you, the sine conversion there. The next part that we have to look at is what we call the linear magnification, or what we call the lateral magnification. So you can write linear.
Yes.
Linear, lateral magnification. M, produced by spherical mirrors, produced by spherical mirrors. Now we have not derived the formula for finding the mirror formula using a finite object. And I remember I gave you an assignment before this lesson. I told you that you derive for me for a convex mirror using finite object. Eh? Steven, are we together? Eh? You derive for me and you send it on WhatsApp.
Yes, teacher.
Even Sandra, derive and send it on WhatsApp. If it needs, you may do some little research and find how it is derived, but derive and you send it on WhatsApp, and also practice because those questions are asked. All right, now, what is linear magnification or lateral magnification? So this one is just the ratio of the height of the image to the height of the object, full stop. So linear magnification. Members, we are using linear magnification. Later on, we shall see that there is another type of magnification when we are looking at lenses, and also when you're looking at optical instruments. So, but because you're looking at mirrors, so we look at linear magnification. So this is the ratio. It's the ratio of height of image to height of object. Stop. And then you can proceed and say M is equal to height of image, which can be HI, and then out of height of object, which can be H naught, like that. So that is the correct definition of linear magnification. That's the correct definition of linear magnification. But there are other definitions that you can give to mean what linear magnification is. So you can say that also linear magnification is the ratio of the image distance to the object distance, as we see here. Or you can also say that linear magnification is the ratio of image height to the object length. This one, image height to the object length, can also define like that. This one, we look at, image length to object length. So let me write that one down, linear magnification, and I will tell you when we use it, or when it is used, is the ratio of image length to object length. So normally this one happens when we are looking at an object which is just, let me say, lying along the principal axis. It is lying along the principal axis. It is not vertical, but it is lying along the principal axis. So if you have the principal axis drawn there, so there is an object like a pole just lying on the ground there, and it's the object. So there is a mirror here, and then they're asking you where is the image. So for that case, we just have to define magnification as the ratio of the length of the image to the length of the object. So the ratio of the image length to the object length. So you write image length to object length. We shall look at all these calculations, I think, in the next session or lesson. What else have I left out? Okay, linear magnification is the ratio of image size to object size. You can also use that and then work out. Now, how do we derive linear magnification? So in the diagram that you have on the left-hand side, they are saying that consider the incidence ray AP on the pole, incidence ray on the pole of the concave mirror from an object of height h placed at a distance u. So this is the object placed at a distance u from the mirror, and then it is reflected back. So the ray that comes from the top of the object is reflected back, making the same angle with the principal axis to form an image of height h located at distance v from the mirror as shown. Now, because when you're driving, all these terms are very important, because you find what AP is, you have defined what U is, you have defined what H is, and you have also defined what V is. So you write these words that consider an incident ray AP onto the pole of a concave mirror, and we are using a concave mirror, but it's coming from an object of height h naught at a distance u from the mirror, and it is making an angle theta at the principal axis to form an image HI at a distance V from the mirror. Then have the diagram drawn. If this is the diagram that you have to draw, it's any other diagram. So Then what you have to do is this ray which is added here, ray CA, they're not talking about it in this description here, in the first description. So it is just drawn for us to know that the image is formed here, because where these two rays meet, that's where the image will be formed. So that means that the next thing that you have to do is you have to look at the ray AB, AP, and P to B. Look at those triangles first. The first triangle is OAP, and another triangle is IPB. Those two triangles. So when you look at triangle OAP, it means that the angle which is theta here, so when you use tan, so it will be H0 over OP, which is U. So this is what is here. I don't know whether, members, is it okay? Do you want me to write this? But I think you can follow here. If I try to zoom in and explain for you very well there. So when you are using that triangle, OAP, draw the diagram and use the triangle OAP. So it means that the tan theta, it is automatically equal to theta because those are small angles. So it is going to be equal to H0 out of OP, but OP is U, isn't it? And also when you use triangle IPB, so the tan theta for that triangle which is inverted, this triangle at the bottom, the tan theta is equal to is approximately equal to theta, and theta is equal to IB, but our IB, I'll write it as H1 over V. Okay, now we have equation 1, and we have equation 2. So the next thing that you have to do is have to equate these two equations and then find the magnification. So if I equate these two equations, I'll have H0 over U equals to HI over V. So cross multiplying there, I'll have V over U is equal to HI over H0. And we have seen that magnification is given by V over U, or magnification is given by in terms of the height of the image and the height of the object. Now, the other thing that you have to know is that we can also get magnification from the Miller formula. So we know that if we are using the Miller formula, so using 1 over F equals to 1 over U plus 1 over V, then we can get magnification in terms of U, or we can get magnification in terms of V. So if I want to get magnification in terms of U, so what I'm going to do is I'm going to multiply all throughout by V, so that V vanishes. So if I multiplying all through by V, so it means that I have V over F equals to V over U plus V over V. Okay, so here I will get V over F equals to V over U plus 1. Now, what is V over U? This is the magnification, isn't it? Image distance over object distance. So V over F equals to M plus 1. And from there, I can make magnification a subject and say M is equal to V over F minus 1. And this one here will give me, will give me the magnification. And this is in terms of V, or image distance, in terms of V or distance. Then if you want to get it, if you want to get the magnification in terms of U, let me request Stephen to lead us. Stephen, in terms of U, lead us. I'm going to multiply all through by what?
By U.
All through by U. So I multiply all through by U. So I have U over F equals to U over U plus U over V. So it means that I have U over F equals to 1 plus. So this one is V over U. That means that that is the reciprocal of 1 over what? 1 over M. Are we together? Are we together, members? So I can say 1 over M equals to U over F, then minus what? Minus 1, like that. So if I want to make M a subject, then I have to find the LCM on this side. So I have F, and I'll have U minus F equals to 1 over M. So it means that if I take the reciprocal on both sides, so I have M, which is equal to F out of U minus F. Okay. So that is the magnification. That is you can use this or you can use that if you want to get the magnification in terms of U. Okay, in terms of what? Members, I would like the lesson to end here. We shall meet next time, next week. Have a good day and bye.